Welcome to my talk called Go Microservices and All the Joy. There might be some irony on some of the slides. I didn't include it in the subject, but be warned if you're allergic to irony and sarcasm, be warned. My name is Andrzej Grzesik. I know it's a bit complicated, so my Twitter handle is much simpler. And I know this is the last session of this very long and I enjoyed it so far greatly, but I'm also quite exhausted conference. So if you want to talk to me, I'll be happy to have a conversation immediately after the talk, or if you have to run to the airport because you have an airplane to catch, feel free to drop me an email, tweet to me. Of course, you might go to my blog and try to contact me through there as well. A couple of things about myself. I come from Poland. I used to lead the Polish Java user group. Now I do it remotely via email. I also am related to Kraków Hadoop user group, Software Craftsmanship Kraków, a conference called Geekon, and I also am a Java champion, which probably is something that you haven't never heard of. It's something similar to Microsoft's MVP, if I understand the concept well enough. This session is about Go and microservices. And to give you some background, I've been using Go since 2013. I've been working for a particular auction site. You probably have heard of it. The name is 4 letters long. And the project that we've been doing is, well, we were basically changing how some static assets are being served in that infrastructure. The story is, if you go to any large website that has rules and regulations and help, and it serves a number of nationalities, and it has a large amount of traffic, well, they will have to have a separate infrastructure for serving static assets. That's natural. And we started to redesign the whole approach, which used to rely on a number of Drupal instances. We wrote the whole thing using Go, not only, but the front-end serving part was using Go, and we were extremely happy with how it performed. Since then, I've become a fan of the language, and I wanted to tell you a bit more about it, what it's good for, what it's bad for, because it's not a silver bullet. I am not advocating you abandon all the languages that you already know and you're using for other things and you're happy with. Go is good for certain areas. It's not a perfect thing. It's not a thing I would definitely use everywhere. So, Go. It is a relatively new language, and it was first announced to the world, I think, in 2009, if I remember correctly. Since then, it has gained a lot of popularity. That's a screenshot from Tyobe Index. Screenshot is relatively recent. It was taken yesterday. So you can see Go has the lucky 13th position. Within the last year, it jumped from position 54 to position 13. Of course, somebody might say Tyobe Index isn't really relevant to anything because it's based on what people search and what advertisements there are. So not super useful, not a very scientific method. But we don't have a good way or a great way to compare programming languages' popularity. That's one of them. Another way in which you could see how popular it becomes is to look at Stack Overflow, how many questions about Go are there, and the number is increasing tremendously. You can see that it's already, well, it almost has taken over Ruby. Probably within a couple of months it will take over Ruby, and then Delphi, PHP, assembly, all within 7-8 years, because it's 2017, the beginnings, and it was announced in 2009. So the question is, why should you even look at Go? Why can't we write all the software in the languages that we all have been having since we started? I think if I remember correctly, John von Neumann was perfectly happy with people writing machine code. As you know very well, we are not using machine code too often. We are writing in languages that offer us better abstractions. So if you look at the Go's website, some reasons, some rationale for the project is, well, first, computers are quicker. The hardware that I'm running on my phone is much faster than the desktop machine I was having 10 years ago, which is scary. I have more RAM on my phone than my first computer had of hard drive. That's insane in terms of progress. The thing is, software development, which means us, humans, usually we are the bottleneck. The languages, the paradigms haven't really changed. a lot. We still do very same kind of loops, very same kind of orders, very same kind of instructions. And hardware that we run the software on, it has changed tremendously. If you take a look at this slide, that's how many, this is how many cores did every server CPU released from Intel had since 2006 up to 2016. I basically just went through arc.intel.com, which is a website that has all the technical specifications for the CPUs, and then plotted them onto a graph. You can easily see that there is a growth, there is a huge growth in the core count, and you can safely assume that this growth will continue, which means we will have more and more cores, and programming for a single core, as you very well know, is different than programming for 24 cores. If you've been to yesterday's excellent presentation about being quick and running fast while being friendly to the metal, then, well, you might know why we have to write code differently for multiple cores, because all the story about caches and memory sensitivity and read writes and memory bandwidth has been explained there. But basically, what also Go project has managed to capture is the emergence of multicore computers has generated worry and confusion. Because one approach is to use locks and mutexes and do software controlling threads manually, but it's difficult. This is hard, this is difficult. Who can write trouble-free multi-threaded programs here? And is absolutely certain they will work immediately. No hands. Yeah, I can't. I make mistakes. And the worst thing is those mistakes are sometimes hardware specific. Sometimes they only manifest themselves if you have, let's say, 2 CPUs in a box. Sometimes they only manifest if a CPU has a specific number of cores, because those are very strange problems, things that we humans are not really great at identifying, and that's not natural, at least for me, to think about. Another thing is, software projects become bigger and bigger and bigger. You probably know and work with some very large systems, very complex systems. And there is a natural trend in the world that we will need more programmers. We've all heard about all the initiatives that want to bring and invite more people to start coding. And if you want more people to code, then you naturally introduce a bottleneck. If I'm programming with one of you, we need to communicate. If we want to program in a group of 100, there will be more bottlenecks. So there is a law, a very famous law that's called Amdahl's law. It's illustrating how much speed up can you get by using multiple execution units, depending on how much software is parallelizable versus how much cannot be made to run in parallel because it's serial. So as you can see, the performance isn't going to grow linearly. It's not going to grow straight, and there is a natural barrier even if there is a 95% parallel portion of our software. So if just 5% means we can only get around 20 times speed up, which means obviously adding more and more execution units, translating to cores probably, isn't the way if we keep having serial elements in our software. And we've known that for a couple of years, and things such as CAP theorem have been around, have gained a lot of weight. They are things that we all talk about. Consistency, distributed systems, distributed databases, they are a thing because we cannot do multiple phase commits over large clusters of any database servers. Well, despite what the salespeople from Oracle and MySQL and Microsoft SQL Server would like us to believe. It's not possible. And there is a solution to that. This solution, one of the solutions, was identified by Mr. Hoare a number of years ago in a paper called Communicating Sequential Processes. The idea is we shouldn't communicate by sharing memory. So we shouldn't have one piece of memory that we will share and protect access to. Instead, we should share memory by communicating, which translates to share the messages. Let's exchange messages between threads, between your execution units. Don't build artificial barriers because it's hard, because it doesn't scale. It's hard to scale. And now, more than ever before, it's something that's actually speaks to us very, very strongly. So I did mention Go, and I do mention microservices, and it will hopefully all come together towards the end of the talk. But how does Go approach that? Well, Go has the notion of channels, which are pieces of memory in which you can, thread-safe pieces of memory into which you can put and from which you can read specific objects. So if I want one Go routine, which is the equivalent of a function running in a thread, I can put it into a channel. If I want somebody else to read it, they can do it. What Go runtime provides is channel will be thread safe. Channel will have all the necessary memory barriers, so you don't have to risk false sharing. You don't have to read reads that only read half of a long because something. No, Go runtime provides all the guarantees, but it takes something in exchange. You don't get control over your threads. You don't get direct control over your execution units. If you want to control which Go routines work, you have to use channels for that, or you can use some other concurrency constructs, and they are all listed in the documentation. But the idea is you don't write threads. If you've written any PHP, have you? Let's assume you have read about how PHP handles web requests. A web request comes in, and a specific thread in an application server will handle everything, and there is no sharing. And that scales perfectly. And for information, I haven't written any PHP. It's just a useful illustration. That means that nothing has to be shared. If there is something to be shared, you just send the data to a database, probably, or to something else. This means that there is no way in which somebody can make a mistake about concurrency, about serialization, about anything else. That, for Go, allowed us at the mentioned auction site to handle all of the traffic that was accessing those help and other static content sites by using just 4 machines. Before, the number of machines was way higher. I think the default was 9, and it was going up to 20 or 30 machines. With Go, just by rewriting the application, by not using things that would share states, we ended up with just 4 machines handling and having enough bandwidth just to handle with all the spikes. Moving on, another important idea behind Go's creation is some fundamental concepts such as garbage collection and parallel computation are not supported by systems languages. And they mention systems languages, and systems languages means here C and C++. Because in Java, in C#, we do have garbage collection. We're very happy with that. We have parallel computations. That's easy to do. You can use actors. You can use akka in the Java world. You can use akka.NET in the CLR world. You can use other actor and other frameworks. Whereas in the closer to metal systems, you don't get that. There is no decent, there are garbage collector implementations for C. You can do reference counting, you can do smart and auto pointers, but it's tedious and it's error prone. And if you've written software with that, you will run into problems, sadly, if only because somebody did something that's not totally expected. So designers of Go decided that memory garbage collection and not having to worry about how memory is accessed is much easier, because this allows people to write software in an easier way. And remember, at least I look at people as the limiting factor when it comes to writing software at times, so that simplifies everything. So Go is easy, and Go is also super fast. If you've, who has been writing and working with large systems written in C or C++? Anybody? So let me tell you a story. Well, I used to work in a system that was taking care of crew management for an airline, or a couple of airlines, actually. The whole build was taking a day. So 24 hours when you wanted to deploy, come up with a new version. So you write some code, you press compile, you go home. You come back on the next day, see if it went through. If it didn't, you fix the error, try to press compile again, and then go home again. And that was on a large multi-core, multi-CPU machine. So the system was large and took forever to compile, because C and C++ compiler with what's happening in its compiler pipeline isn't just designed with speed at first. Go, on the other hand, was designed as a language that should be easy and as a language that should be fast. So it compiles almost immediately. That's very important in Google, where Go comes from, because they do have a lot of code. I don't know how much code they have exactly, because I have never worked for Google, but our software, the one on at the mentioned auction site, which name I'm trying to avoid, but you can find it on LinkedIn, usually took below 2 seconds to compile, every single time. And there's a question, I think.
How does it compare to Java or C#?
So how does Go compilation speed compare to Java or C#, or do I understand you correctly? So when you compare it to Java, it's faster. When you compare it to C#, I would say it's also faster. And there is a crazy idea that designers of Go decided that if you want to have any dependencies, you will compile them along the way. So despite compiling all the dependencies that you have, it's fast. It's really, really, really fast. Of course, I can repeat really an arbitrary number of times, and that won't give you anything. But you can take any project from GitHub and then try to compile it, and I haven't found anything that I had to wait for the compilation to actually happen. Of course, yes, I work on powerful machines. I work, this is a MacBook Pro. The desktop I use at home is powerful. The workstation I use at work is very powerful. But it's a couple of seconds, and that's it. I mentioned dependencies. Designers of Go also decided that dependency management is a problem. It's a problem because when you use Maven or NuGet or whatever other dependency management tool you want to use, I'm not even looking towards Node and LeftPads, the infamous issue, you have problems because you have to download the internet, and then every single time you do it, you don't know what you get. With Go, the default dependency manager that also comes with the toolchain that you install as part of Go SDK will just get the sources of a particular library, which means you will compile what you will run with. And that will be statically linked, which means you will produce a single binary, and then that binary blob can be deployed, can be distributed among, your cloud of machines, your any number of workers that you want to run with, and that's it. No dependencies, no runtimes, no specific libraries that you need to install, because everything is contained in the target program binary that you wanted to create, which, if you work with large environments, it simplifies a lot. If you work with small environments, it also simplifies a lot and teaches you that you only have one thing that you have to worry about. And we'll come back to that later. So release cadence, I mentioned Go was announced in 2009. A new version comes out usually every half a year. And then somebody could be afraid, like, what about compatibility? What changes between separate language versions? Because if you look at Java or C# or other languages, there are major changes sometimes. Go mostly changes tools. It adds optimizations. It improves runtime. It doesn't add a lot of language features. So you usually get to see no language features being added between version to version, which means what you get now will be 99% of what you will have in a couple of years, most probably, which means you can learn Go now and you're good to go. No pun intended. Of course, the libraries will be changing. The libraries will be evolving. No new things will keep being added to the ecosystem. But the language itself, the core platform, is relatively stable. The improvements are all around, and the improvements are under the hood. So in the runtime, in how GC handles and behaves, in how much latency the GC is dealing with and causing. And I mentioned GC. If you've worked with other managed platforms, GC can be a problem. Latency, if you want to control it in Java, that's almost like a dark art. How do you configure, how do you tweak your garbage collector so that your latency, the pauses induced by garbage collector are less than hundreds of milliseconds? It might be some tuning. You might also get some very smart consultants to do it for you. They will do the job, but it requires a lot of knowledge. In Go, the exact amount of GC tuning that you can do is limited to the amounts of memory that you can dedicate to the process, and that's it. The decisions have been taken and made for you. Focus is on latency. and there are no tuning handles, which means you're happier. Everybody is happier, because if focus is on latency, which means services will have to respond faster because the whole application shouldn't block too often, or if they block, they shouldn't stop the world for too long. You don't have to basically do a PhD just on the subject of GC tuning. Moving on, I mentioned it's opinionated because things such as formatting, that's already decided for you. There is one official Go formatting. It's using tabs, it's putting curly braces in very specific places in a line. There is also a formatting tool as part of the default toolchain. So you don't get to decide, you don't have to waste your time discussing that. I mentioned dependencies. The approach with dependencies, if you have a dependency, just take it, compile it with your application, and this is the whole thing. This is all statically linked together, so it's easy for deployment. If you want to reason about what went wrong in the application, you get the sources. You don't have to look at what are the sources of this library that I downloaded from the internet in a compiled version, only to learn that somebody maybe, I don't know, accessed an artifact repository and removed all the sources, or actually the version that's deployed doesn't really reflect what's in the source tree. Those situations have happened. They have happened to many of us a number of times, and they are very unpleasant situations to debug. Go doesn't have it because you'll get an ease of deployment and ease of reasoning of what's actually running because there is only one binary. And microservices. This talk is about Go, the language, and microservices, and the question is, why do we even look at microservices? What's wrong? And why? What's the idea? Is it just because I wanted to put two popular terms in the subject of this talk? Of course not. Software, in general, is hard. It's non-trivial. Somebody could say, why? Why is software hard? Or which aspect of software being hard I want to tackle in this very talk? I'll focus on the human aspect. I tend to say software is a people problem. So no matter what is the number of 10 or 100 times programmers you have in your team, if you have a large project to deliver, you need many programmers. Which means, well, we are limited by the very same law that we've seen, which limits how our software runs and what limits the performance of our software. It's Amdahl's law again. If we all have to talk in order to be able to deploy something and deliver something, that means we will be limited in performance if we all want to release one large chunk of work. Testing that large chunk of work is a serialization step, which means it will be slow. If you look at different pieces of functionality, why should my configuration system be dependent on somebody's catalog system? Why should my catalog system be dependent on the search? I just want to release something that, well, manages, I don't know, the HR accounts. HR accounts are independent of orders that some kind of e-commerce website does. If we are building a monolith, then we all have to be ready with our pieces of code in order to be able to compile, then to test, then to deploy. If we split that, naturally, well, we get the speed up because we start being able to deploy. Somebody, well, Subu said that independent deployability is the primary driver for microservices. Every other driver is secondary. That is a very strong opinion towards one direction. And I can agree and disagree at the same time. What I would add is independent deployability as a goal, yes, but what is enabled by being able to independently deploy is I can work independently of another team elsewhere, which means we can go our separate ways. We can add features our separate ways and add the speed that we want to both work. And that also means a large number of people can introduce a large number of changes to the same project, the same system, to be precise, because a large system can become a number of smaller projects, which means we don't have to wait for somebody else to deploy their part of changes so that we all can deploy and release and use the new awesome functionality that we wanted to deliver. And software is only useful when it's working, when it's running. I am a huge anti-fan. I despise writing software that doesn't get used. I think it's a waste of time, unless you're learning something and just experimenting, and many people do the same. There is a number of companies that artificially limit their release cycles to, let's say, twice a year, once a quarter, and sometimes, well, something like that. Of course, right now we all talk about continuous delivery. We start to deliver software more and more often. Well, Windows 10 is a great example of what a change they have introduced. They started to release new builds of the system, especially with the early access, much more often. But a large number of software projects are still delivered rarely. If you have a large system, you will have a number of dependencies. The ability to change one dependency and to move forward with one dependency independently of the other is extremely powerful. And big systems are hard. And the bigger the system is, it scales with the number, well, with the size. I could say quadratically, but that doesn't give it. It doesn't give it justice. Big systems like Google. And there is no single person on earth that understands the whole of Google. There is no person on earth that understands the whole eBay, how everything at eBay's systems works. There is nobody that understands the whole of Facebook because it's just impossible. But that also means that if we cut a microservice, if we cut a piece of software that just does one thing and one thing only and one thing well, we are able to comprehend. We, humans, can deal with software that takes order, talks to the shipment service, to talk to the warehouse service, and then does whatever is needed. Maybe prints labels, maybe also reserves some instances of a certain product so that the delivery guy can throw it over the fence of your neighbor so that then you get to talk to the neighbor, but that's beyond software problem. And understanding and being able to change the system and being aware of the system leads us to something I call software discovery problem. I don't think it's an official term, but I like to use it because it's something that's to do with how do I know that there is a piece of software that does what I want to do. If I want to add two numbers, I will not think whether there is a library for that. That's trivial enough. I will just do it. If there is a problem of padding things from the left, then if I'm in the JavaScript world, I will in no way be able to write it. I will, of course, have to use the library, and then if that library, something happens to it, well, we are all doomed. In a large organization, like my favorite auction site that I keep mentioning, how can I tell if there is something that verifies client's address, client's phone number, client something? Well, the answer is, well, I don't want to know about it. I don't probably want to write something that's probably somebody has written before, given that they have exposed it as a service. And services lead us naturally towards APIs. APIs which are hard, because APIs mean governance, and and governance means you need people that will look after the APIs, and you need people that will look after the overall shape and what's possible, what's available, what's there. And there was a very smart person called, the surname is Conway. I think his name was Michael? Huh? Melvin, yeah, so my bad. At least you agree on the surname. That's half a success. Organizations design systems which are similar to how organizations work, which means APIs will reflect how organizations are designed, which means if your organization has an artificial boundary or a natural boundary, let's say a huge development office in London and a huge development office in San Jose, then the software will reflect that. It can be a good and it can be a bad thing at the same time, because the APIs will be very friendly towards everything that's internal, which means everybody who works with me in the same office. There will be great APIs for, let's say, doing contacts and payments and shipping. And then poor guys on the other side of the pond will have to deal with something that we actually never thought of because they don't even exist in the time zone that we are mostly in. And that's unfortunately visible. The great thing is, with APIs that are exposed as REST, as JSON or something like that, you can actually write it down and produce a web page, produce a catalog, produce a service that will say, well, those are our corporate APIs. This is what you can do with our systems. If provided you have the right permissions, you have the right data to put in, this is what you can get out. This is also what you can check the catalog, you can check the pricing strategy. There was an excellent talk yesterday called Microservices Mega Failures, if I remember, or Mega Disasters. If you have the time, I would recommend you watch it because, well, it did mention a couple of things I wanted to mention in here, but it's already been said at NDC, so there is no point in me repeating that. But that's a good talk. It mentions some of the problems that are visible when you have a number of services in a company. And there are also some things that will be repeated, like network problems, like tracing, like logging, like debugging. If you have a service A, calling service B, calling service C, calling service D, you will get into a number of problems. How do you solve it? Should you write a software that will allow you to do it easily? I would argue that you shouldn't. I would say don't. I would say use a framework. Let somebody else fix the non-essential problems for you. This is why I love that's a framework in Go for building microservices. It's called Go$kit. I like it, and it has integration into a number of things that are useful or even essential when building microservice. I wouldn't advocate that you try to reinvent the wheel because, well, you can solve more important problems in your business. And again, we talk about microservices. Let's take a moment to look at this quote. So there is a pattern I noticed. Anybody who starts working with microservices soon starts to look at things like Kubernetes, DCOS, consistency protocols, Paxos, maybe Raft, maybe something else, and etcd. How do you share configuration? How do you do something else? Maybe you should write our own tools to do our own cloud, our own microservices, our own containers. And the scary thing is, no. There are solutions available from all the major cloud providers. There are open source tools that do it for you. Just use them. Don't waste your time. Don't waste your breath, because our business, our industry will move on. And yes, it will be great fun, but that's not the point. If you want to look at what's currently available, a cut through the landscape, there was a talk today by Michelle. I dare not pronounce the surname, about Docker platforms. So many Docker platforms, so little time, because there is already a number of people who are doing platforms for running Docker. And I'm saying Docker because that's the reasonable default for most of people right now who want to do containers, but you are not restricted to running Docker. You don't have to use Docker to run microservices. You can do microservices with something else. Running Docker is not mandatory. It's just a useful thing because it allows an arbitrary thing to be shipped with the operating system and just spawned. And protocols. The quote I have shown you before mentioned REST and mentioned JSON. And JSON? Should we do everything with JSON? Well, JSON, there is a genius quote about using JSON for everything in the internet. I think it says something about the internet right now is running in debug mode, because you can just examine it with developer tools, and all the microservices, all the services that talk JSON one to each other, well, it's not efficient, it's not space efficient, it's not fast, the latency is less than ideal, it's constrained, you cannot do comments in it, it doesn't have a support for any kind of schema. Should you use it for everything? Maybe, maybe not. There are other formats. So protobuf, yes. XML and SOAP services, yes, of course. REST is not very important. What is important when talking about protocols and formats is to specify what you are exposing, what is the contract that you are providing with your service, what you are going to respond to, what's the service level. And that is important because protocols and contracts allow new stacks to be built. And I will say new stacks because new stacks will keep taking place. Some people prefer to be constrained to their own corporate framework. Some people prefer to use something very, very, very specific and very arbitrary. But software and capabilities in the world are moving tremendously quickly. I would say that tying to a stack, tying yourself to a stack, tying yourself to a probably corporate stack, is a monolith in disguise. Why? Because of course we can try to say that progress will be when we split that one huge monolith into a sea of services, and now we have achieved microservices. This is better than Zen. We're done. But no. Because when you have a corporate framework, when you have an arbitrary framework, that is the only thing that you can use in your environment, when it's a very heavily opinionated and very heavily invested in framework, you can't change any part of the system without actually making the framework support it. If you cut yourself away, if you are restricted only by following a protocol and then talking JSON or XML, something, protobuf, to other services, you're fine, because it can be a Node application, it can be Java, it can be .NET, it can be Go. Which one should it be? I don't know. There have been enough flame wars on Stack Overflow and blogs that we don't have to have another one in here. The reality is there are tools which do certain things best in specific languages. One trivial idea, one trivial problem is machine learning. Right now, machine learning, if you're going to do machine learning, you're probably going to do some R. You're most certainly going to use some Python. That's almost guaranteed, which means nobody is going to fight a holy war that we shouldn't do machine learning in Python because we are, let's say, a C++ shop or a C# shop or a Java shop. We will not touch Python. No, these tools, the solutions are in Python. You will use Python because that's how it comes, which means if there is a corporate framework that we have to make it support our Python infrastructure, well, it will be a lot of work. Half a year later, maybe 12 months later, maybe some more time later, we will be able to make some change. In the case of the mentioned auction site, they do have a corporate framework. They do have a number of pages that rely very, very heavily on the mentioned corporate framework. They have run themselves into a problem. They can't change a number of pages dramatically. They can't introduce new things as quickly as they would like to because the framework ties them. It's a very old, very heavy, very cumbersome right now thing, very non-modern. And because people just let it be, it was left alone. And also because it's cumbersome, because when you cut things into a number of services, some people might go and say, well, you know what? We could put this service into next to this one, next to this one, next to this one, and have it all running in a box. And system in a box is a huge anti-pattern. It's a scary, scary thing that is a thing. People do it. A number of companies have been through that. How it manifests itself? Well, they buy a very beefy server. They give it to the developers. Developers do their magic, do their rituals, do their water dances around it. They deploy a system, and that box is the only instance of a certain well-known provider of something. That's a thing that we can discuss outside of the room when nobody's recording. And that's what the system is. It's the thing in a box because nobody designed it, nobody tested, nobody took the time to cut it into separate places, into separate things, because latency. Because if you have different machines, if you have different virtual machines, different systems, you will have serialization, you will have problems of network latency, you will have problems of what runs, what breaks, what's the probability that my service call that allows my user to sign up will actually succeed. An excellent example made yesterday in the Microservices mega disasters talk was just multiplying 99.9 SLA, well, availability of every service. If you have to go for a number of services, well, there is a very little chance that nothing will break while you're trying to run a query. So watch the recording when it's available, avoiding microservice mega disasters. So a framework, well, another quote, delayed cost of decoupling is high. So yeah. Because we have a corporate framework, everybody uses that, it would take a lot of time to actually go and disentangle that mess. So taking a framework apart takes forever. So but nobody does it, which means in the end, it will limit business agility. It will restrict organizations' ability to change its direction, to make changes to its website, to its estate, to everything. And now we can come back to the question, or well, try to marry. Why would I advocate that you should do microservices in Go? First part is that there are good tools for Go. It's a mature solution. It works in a number of places. It powers a number of solutions. Code is relatively easy. I'm not showing too much code here because I respect you are very smart people. You know how to use Google. You know how to go through language tutorials. You know how to do it. There is no need for me to teach you how to use Go. You can do it in your own spare time. The idea is that Go is happy with its scaling, making performance software. It's great at it. Its type system is simple. People who used to write software in C, C#, Java, Scala can pick it up almost immediately. In terms of popularity, it's only growing. So if the only thing that you're looking or you're going to look at in a couple of years is job security, it's great. The number of developers, the number of projects that Go is taking place, that are using Go, is constantly increasing, which means sooner or later you will use Go somewhere. So it will be useful to have it available to you. And now, an important point is, where would I say you should use Go? If you make a decision to actually try to learn the language, one of the first tutorials that you will see is doing a hello world, and then probably a telnet server, a web server, something like that. It's amazing at doing services. It's amazing at doing middleware. It's amazing at doing things that talk to the network. It's just great at that. I have never written a UI application with Go, and I probably wouldn't try. I probably wouldn't try to power a web framework with Go because I prefer richer type systems for the business backends. Because richer type systems, for me, in the back, they offer a certain richness which pays off in time because of course you can do DDD, you can introduce types and type hierarchies in Go. It's just I prefer how it works in Java and Scala and other areas. However, if your solution has to do something with taking in traffic, maybe combining a number of queries and then coming up with a response, maybe orchestrating other services, maybe talking to a number of backends and then combining the responses, Go will be perfect for that. Its approach to concurrency, its approach to multi-threading, the fact that you don't get to do multi-threading, the fact that you have to communicate via channels, means you will not have to debug the software because your multi-threaded code has errors. Because it's simple to reason, and it's performant, and it's fast. And it's also very, very easy to reason about. And if you need to scale that, just put it on a more powerful machine. The fact that you're not blocking, the fact that you're not using using threads directly means that you don't have to worry about, and you will only allow Go framework to run with a certain number of execution threads, and everything else will be taken care of. And so, because you will probably, hopefully, look at Go, and you will probably want to read something about microservices, those are the books I would recommend. Go programming language, naturally, because a good language tutorial is useful. It's a great book. Microservices in Go is a book that's still in production. Out of what will be on the market, because I think there is another one being done by Pact, and I've seen mentions of a third one being prepared somewhere. This one looks like the best position that will be on the market. I'm saying will be because it hasn't been finished, and sadly, an early access version isn't available just yet. Release it, because when you're building microservices, you have to know how to make microservices and systems reliable and resilient, and make sure that they actually, from end to end, work. And enterprise integration patterns. That's a classic. That's a classic about doing message-oriented middleware and building systems that rely on messages flying back and forth. Because when you're doing microservices, you will have that's effectively what you have to deal with. A number of independent runtimes, more or less dependent, that sometimes have their backends exposed to themselves, sometimes not, but they will talk via messages through APIs, through Kafka, through message buses, through databases. And the patterns that some of them have already been designed. They also solve a number of problems, and there is already a book about that, so I can only recommend that. And with that, I will say thanks, because I know some of you have to run to the airport. Thank you very much for coming to the last talk of the day. And if you have any questions, just raise your hand or shout or approach me. Thanks.